Welcome back, HVAC innovators. Here we are. So, day 29, we've covered model 0, 1, 2, 3, and 4. I actually don't really know much about this one, but it's model 4 discussed in the PNNL paper. I think it's advertised as some kind of saturation and coasting model. It looks like there's model situations where heating slows down as it nears set point, useful when the last few degrees are disproportionately longer. So let's see how we do this through math. Like I've said before, like this is mechanical engineering theory for the mathematical models to optimize HVAC start. And we've been going through these couple different model equations. The last one we did was this little one that's a little bit more complicated, requiring some linear algebra. And then this one is a first order response physics driven model. I actually don't know much about this, so I'm kind of going into this a little blind. The other ones I studied a little bit ahead of time, so let's see how hard this one is. So Model 4 uses a first-order thermal response model derived from building physics instead of a pure curve-fit regression. It assumes the zone behaves like a first-order system and estimates time needed to reach set point based on how temperature actually responds after the unit startup. Optimal start time is computed using this equation. Looks like alpha A is acceptable temperature tolerance, deadband. B parameter is initial temperature difference between zone and set point. And C is a dynamic system response factor, continuously updating using least squares learning from historical recoveries. Interesting. So, yeah, let's get into this. I guess in the paper, I just want to take a note of it. This is how Model 3 is described in the paper, which we did this. This is our multiple regression equation right here. Alpha A, alpha B, alpha D. Then model... Yeah, this is kind of interesting. I definitely recommend reading this. So like the model 4 is this model 4, the fourth model, uses simple first order response to predict response time. First order overall response model is simple closed form solution that can be used to predict the time to reach a new set point, shown as in these equations. Response, let's see, after the R2U starts, continuously updates its parameters based on the deviation between set point. So, let's just read this. So, the first parameter, alpha A, is a constant value representing an acceptable deadband. Yeah, which is exactly, it looks like the AI pulled this right out of the paper and put it in our AI-generated coursework. While the second parameter, alpha B, denotes the deviation between set point and zone temperature. And the last parameter reflects the changing conditions, the dynamics calculation based on the air variations over time after the R2 start. It uses least squares approach. I still have to wrap my head around this a little bit. So hopefully our AI generated lessons can help us understand. And then at least for me, when I look back on these equations, it makes a little bit more sense. Okay, let's close these windows. So day 29, thinking like a capacitor, which is kind of interesting because that's like electrical engineers' forte. The capacitor stores energy. It says right here. So in electrical engineering, a capacitor charges and discharges exponentially. Buildings behave similar. They warm up quickly at first and then slow as they approach set point. The analogy leads to the logarithmic models, where the time to reduce the error follows time is approximate to the log of, I think this is error, basically. Recognizing this behavior prepares you for your Model 4. Okay, so here's our mini Python script. I still have to get to our, open up VS Code here. Feel free to reach out if you ever want any help getting Python set up. There was one video we did that in the beginning of just getting Python set up, and then I'm running everything in VS Code, which is something that you don't have to do, but even when you download Python, or there's even scientific, there's like Anaconda Python, so there's a whole bunch of different options. Feel free to reach out if you ever want any tips or anything getting set up. I just kind of like using vanilla Python. Some people like using Python in the browser for IPython notebooks, which are really nice for data science. Excuse me. But I kind of like just using like, this is more of like a vanilla Python environment, where it's, in the first video getting Python set up, it was just like a very stripped down version of Python, no scientific packages or anything. It's more of like kind of a computer science approach, where I can do anything in the vanilla Python world. If I want to install the scientific computing libraries, I can, and if I don't want them, I don't need them. And so it's my own preference. And VS Code is actually kind of nice for if you're doing IoT work, or if you're doing web app development. You know, it's kind of a developer-friendly IDE. So feel free to reach out if you ever have any questions in that regard. Okay, so let's just run this. And it looks like our simulation here is just creating some kind of fraction and outputting time, I guess. Oh, these are just different time values, so they're just doing some kind of smoothing right here with the math library. A tau minus t, you know, this. So basically they're taking this value right here and dividing it by here, and a fraction charged, which seems kind of interesting. So I have to think about that, how that would apply to optimized start. What physical properties of a building correspond to a large time constant? Given if the time constant is small, how does the system behave? Give another real-world system that follows exponential behavior. I have to think about this. What physical properties of a building correspond to a large time constant? I guess that's just thermodynamics and heat transfer is where my mind goes. If the time constant is small, how does the system behave? If the time constant is small, how does the system behave? I have to think about that. That means that the system will behave very fast, I think, if the time constant is small. So let's open up our good friend ChatGPT. I'm just thinking of maybe this let's see, I'm trying to think if this is I have to think of like the last video of the window we had open, so I have too many windows open here, sorry. So I know this one is So I'm just gonna go ahead and kind of just get my some of these questions I feel like it's kind of nice to have a teacher, so I knew I would be running into some of this stuff. So we're on day 29. I'm just gonna give it the README for some context. Maybe even give it the PNNL paper. So I'm on day 29 of the lessons model 4 from the paper. What physical properties of a building does correspond to a large? So I would say heat transfer, and thermodynamics, right? Thinking of HVAC load calcs. Is this correct? If time constant is small, I'm going to say very fast, right? Give another real world example that follows exponential behavior. Give another real world example that follows exponential behavior. Oh boy, I'm just gonna say hydraulics. Let's just see what, oh shoot. Okay, so that gets to think a little bit. I think while that thinks, maybe we can peek ahead at day 30. So it looks like we get into this, some of this decay rates, which looks like here. So we take the log of the decay rate. So yeah, it looks like it gets into some of the little bit more the log arithmetic type of math. So cool. So that'll come tomorrow. So something to do that today if this okay, it looks like it kind of timed out, so I might just restart you. Gosh, it's like sometimes ChatGPT goes so incredibly slow. And like, oh, come on. I think that I've used this chat so much that it has just an enormous history behind it. I should have just used a new chat, and it just makes me wonder if like the browser is retaining so much information that it's just really bogs it down. Okay, so you're thinking in the right direction. Yes, it ties into heat transfer HVAC load complex. So building your zone is treated like a first order thermal system. Time, temperature final minus temperature initial, where time constant tau represents how fast the zone moves toward its final temperature. Large tau, big time constant, slow building. Yep, so heat transfer, yes. Thermodynamics, building physics. So what if the time constant is small? It responds fastly, so yes. Very fast, yep, exactly right. So real world systems with exponential behavior, hydraulics is a reasonable analogy. Here's a classic textbook, thermal systems. Yeah, of course. Electrical systems, mechanical systems, fluid systems. So I guess it's all it's all in there. So it looks like, yeah, that was correct. It is kind of tempting just to do this model day 30 one real quick. Maybe why not? Because it doesn't look like it's too hard. So here we go. So let's just do day 30 in a row here. 2 in a row today. So model 4 predicts the time to reach set point using logarithmic decay formula, where deadband is an acceptable error band. 0.5, which is way too small for a real world application. Delta T is the current temperature difference and decay rate, alpha C. Describe how quickly air shrinks from 1 minute to the next as delta T gets small. As delta T gets small, the numerator in log deadband divided by delta T grows, lengthening to predicted time. Well, there's a lot going on in there. So this is it. This is the equation. So in Python form with the math library that's built into Python, deadband divided by delta T divided by the log of the decay rate. Okay, let's run U. I'm just going to delete this. So this is from our other. Maybe we can just comment you out. Predicted time 9.3 minutes. Kind of an interesting equation. Using decay rate of point. Okay, so it wants us to plug in some different numbers here. Put another comment. So what would be our decay rate? Change that to a 5. Deadband is 0.5, that stays the same. Delta T is 6. 15 minutes in our little fake data. Why does the time grow large as delta T approaches deadband? I think that's the whole point of this algorithm, is like the paper, which we talked about in the very beginning of this. As the temperature reaches closer to the deadband, or the actual, as we reach our set point, like it's going to take like a logarithmic form, the slope of that, so it's just going to take longer for it to reach. So that's kind of like what this algorithm or equation is about. So yeah, I guess that's built into the math there. It's taking like a log kind of approach. Explain what happens if decay rate is greater or equal to 1. Let's try it. Let's try 1.05. Ooh, it goes negative. Interesting. So yeah, I guess the decay rate would always have to be a value below 1, or else it won't decay. Yeah, kind of cool. Still kind of curious to ask. I'm gonna ask good old friend ChatGPT, and I know I need to use a different chat because this one is going so slow. So I apologize for that, guys. Come on, add files. Maybe I'll just Let's see if I can ask it without I wanted to upload the file, but it's just going so slow. So if I just go here, go to lesson, and we're on day 30. So for this question, as delta temp approaches deadband and time grows, if the delta temp is small, the differences in a zone temp and set point is very close, and the properties of physics, whatever, and the paper stated that as we approach zone set point, time can take longer, where this equation handles this property of physics better. I'm not describing that very well, but I think it will get the hint. Great intuition. All right, the reason why time grows as large as delta t approaches deadband is baked into the Model 4 equation. So the log of deadband divided by the delta t over the log of the decay rate. From your lesson material, why this happens in plain English, as the zone gets close to set point, heat transfer slows down. That's correct. That's what I meant to say. Small changes in temperature require disproportional more time due to reduced temperature gradient, less driving force, thermal mass, real-world HVAC efficiency, inefficiency near equilibrium. Mathematically, when delta t is closer to deadband, the fraction of deadband divided by delta t approaches 1. When log of 1 equals 0, but as a delta t very closely approaches deadband from above, log of deadband divided by delta t stays positive very far, meaning the numerator shrinks slowly. Denominator of log decay rate is negative. Dividing the negative small magnitude number equals large positive time. So the model is intentionally saying, even though you're close, it can still take a while to finish the last little bit of temperature change. So here we go. Newton's law of cooling, RC network, RC thermal network theory. So cool. All right, guys, I think this is it for today. Just getting into Model 4, which seems kind of interesting to me. So far, so good. We'll see you tomorrow, HVAC innovators.